Okay, so this chapter we're looking at how fast different reactions occur, so the reaction rates, and how we can control those reaction rates. But that's not the whole story. Part of it is we need to figure out why a reaction will occur and some don't occur, or will they occur anytime that molecules come together or only sometimes? So what we're going to look at next is reaction rate theories. So it talks about the theory behind whether or not something's going to react. So we have two that we're going to be looking at, these reaction rate theories. The first one is a collision theory, which talks about when two things collide with one another. The other talks about a transition state theory, where there's like an intermediate that's made, and we got to talk about how that intermediate is made and what requirements it has. Okay, so the first one's collision theory, and this one makes a lot of sense to me. It says that the rate of reaction is proportional, or that there's some direct relationship to the number of what they call effective collisions per second. So here we have that it's not every collision between two molecules that cause a reaction. They have to have what's called an effective collision, one that gives product molecules. Because what it turns out to be is that really there's only a small number of actual collisions that actually cause the reactant to go. They estimate it as like for every billion collisions, you might have one for certain reactions. And so we want to look at why that is. So a couple of things that they like to point out in the collision theory is molecular orientation, which is how the molecule is oriented, molecular kinetic energy, which remember kinetic energy is the energy of motion, and then also the temperature. So let's break these down just a little bit more. So molecular orientation is based on the ideas for that most reactions, two molecules must collide in correct orientation for that reaction to occur. So here they're looking at what's called a reaction mechanism, where you make a little intermediate type thing as a reaction goes. So here we have two molecules. We have NO2Cl, and here's a single Cl, and they're going to collide with one another. But what we want to happen is we want the two chlorines to come in contact with one another. So if they happen to collide, like in this top example where the oxygen and the chlorine collide, that's not going to do anything because they're not attracted to one another. So they bounce off of each other, and that's called an ineffective collision. It's not effective. It doesn't, nothing happens. In the bottom one, though, the two chlorines are oriented in just the right way that they collide with one another. And so you can even talk about if they're at a slight angle, it might not work right. It has to be a head-on collision. You can get very, very specific on these. And because they now collided with one another, then that Cl2 will break off and the reaction will actually occur. So molecular orientation looks at just like where those molecules hit one another, that it has to be a perfect hit for this to happen. Now, the next two things was molecular kinetic energy and temperature, and they're kind of closely related to one another. So we're going to discuss them both on the same slide. So down here at the bottom, we have, so here is the number of collisions that's on the y-axis, and kinetic energy is on the bottom. We've actually seen this before. We dealt with this with temperature, and how we said temperature was the average kinetic energy. So let's look at T1 first. So what this is trying to say is that here we're looking at the kinetic energy of all these different individual molecules. What activation energy looks at is that there is a certain threshold, a certain minimum that particular molecule has to have energy-wise for this reaction to occur. And they call that the activation energy. So they'll say it's EA as they're showing up here. Now, usually this is quite large, so most molecules won't have this. Now, this is kind of like what we were talking about with molecules having enough energy to go to a gas phase. So same type of ideas where they can overcome the intermolecular forces that are holding the liquid together. But here, instead of a phase change, we're actually looking at a reaction. So here again, we have this threshold. So you have to have a minimum kinetic energy for that threshold. So that's looking at the idea of molecular kinetic energy. Where temperature deals with this is if you change the temperature of that particular sample, well, that means that more of your sample has a higher kinetic energy. So therefore, more of your molecules would have enough to meet that minimum threshold to be able to go ahead and react. Now notice it doesn't affect the value of the activation energy. That threshold is at the same exact spot, but now there's just more molecules that can meet that have enough kinetic energy to be able to do that. So that's kind of like the collision theory type idea. Now let's go on to the next one. Okay, so the collision theory more or less stated that the molecules have to slam into each other with enough energy and at the right angles for a reaction to take place. The transition state theory, it kind of goes hand in hand with that, but it kind of adds a little bit more. It says, as this is occurring, that between the reactants and the products, that we have this transition state, or this kind of like an intermediate that's going to be made. So it just gets a little deeper into this theory. So it's used to explain what happens when reactant molecules come together in a collision. And we use what's called a potential energy diagram. So let's look at our potential energy diagram. Now notice we have potential energy on our y-axis, and down at the bottom we have reaction coordinate. Sometimes they'll say time. This is just as that particular reaction starts to progress. A couple things to note here. You note the position of the reactants, where they're at on that potential energy, and then the products. The products would be way down here. During a reaction, they want to have as low potential energy as possible. They want to get rid of that excess energy. If you want to think of it as excess baggage, they want to have a low potential energy because it's less for them to have to deal with. So the more stable something is, the lower the potential energy. It seems backwards when you say it that way, but that's the way it works. A lower potential energy is whenever you have something that's more stable. Now for this one, we have our activation energy still. Remember, we talked about how that activation energy was like this minimum molecular energy that this had to have to make that reaction occur. So we start off with the reactants. We have to have this activation energy. We have to add a little bit of energy to make the reaction occur, and then hopefully it's going to release a whole bunch of energy at the end as it makes its products. The difference between where the reactants and the products are, that is going to be your delta H. Now, if that delta H is negative, meaning that your products are lower than the reactants, that means that you have an exothermic reaction. We're also going to see some examples where, you go up this great big hill and you end up at a higher area, and we'll talk about what happens there. That's going to be your endothermic. Okay, so this is what we want to see. This is the potential energy diagram that we want to see for a particular reaction. We have a certain level for our reactants. We go up over a hill for our activation energy, and then we have a great big slope down to get us to our products. But sometimes we don't necessarily have just that ideal happen. So this one looks at a successful versus an unsuccessful collision. So this first one, this is like if you're trying to roll a ball uphill, and it starts going uphill, but you didn't give it enough energy, so it rolls back down. Well, in this particular theory, this states, you know what, that reaction's not going to take place. We didn't have enough energy to get to the transition state, or we didn't have enough activation energy to be able to, enough energy to pass that threshold of the activation energy. So the reaction does not take place. You have to have enough energy to get up over that hill. Well, again, that kind of goes along really well with both of the theories that we talked about. Okay, let's talk about what happens when it is successful. Let's look at some of the differences that we could possibly have. All right, so this one's going to look at an endothermic and an exothermic reaction. So the one at the bottom, this is the one that we've been looking at the most, where we have a higher level for the reactants. It has our activation energy, this hill that we have to climb, this energy that we have to add to make that reaction occur, and then it releases a bunch of energy to get to a lower product side. On this one, your delta H is negative, and this is exothermic. Exothermic. That's what we're hoping to see. But let's look at the endothermic. Now this could be the reverse of a reaction that we looked at, or we could be looking at just a completely different one. On this one, notice that the reactants start with a really, really low potential energy. Notice how huge this activation energy is. It's absolutely huge. And then when it gets to the other side, it doesn't have very far to go down, meaning it doesn't release much energy. In fact, it releases less energy than what it took to get it started. This is an endothermic reaction. Endothermic. We had to add energy to make that reaction occur. We have a net input of energy. Now again, this could be a forward and reverse reaction. So if you looked and you flipped that diagram around, it could actually be the same type of thing, where it's likely for that reaction to occur in one direction but not the other. Now, this is the part where the transition theory actually becomes a little bit different. This says that during that successful collision, at that high point of that activation energy, we form what's called an activated complex. This is going to be something that's unstable. So if we're looking at that reaction, we might not actually be able to identify that activated complex. It's really, really unstable. But we think that there's this temporary new compound or structure that's made right before it breaks into the products. That's what happens at that top of that the high point of that potential energy diagram. This activated complex is made. Now, if you notice, we actually saw this particular molecules earlier, where we were talking about it had to be a successful collision where the two chlorines came in at just the right angle to collide with one another. And so this says that just temporarily, those two chlorines are going to be attached still to the NO2, and then the two chlorines are going to like pop off of that molecule to form new products. But we have this little in-between area that we have to take care of. That's what makes the transition state unique. Now, the other thing that we deal with during these theories is we look at the size of the activation energy. So you can look at this in either way you want to look at it, where we looked at the temperature diagram, and we said, okay, we need to have a certain threshold, and they said that's the activation energy. The other way we saw it was in the potential energy diagram, where we said, okay, reactants start here, and then we make our products. And this right here is the activation energy. In either of these, there's a certain threshold that you have to have for that activation energy. The amount of that activation energy can influence whether or not a reaction occurs. If you have a large activation energy, that means that on this top one, the threshold's really high, or on our potential energy diagram, that hill that you have to go up is really, really high. That means that it's going to take a lot of energy. So let's see how well I can write today. Take a lot of energy. A lot of energy to break bonds of reactants. And so if you have to take lots and lots of energy, that's going to be harder to do. A small activation energy, well, it's going to be the opposite. It does not take a lot of energy to break the bonds of the reactants. Now, on the flip side of this, so this is how big the hill is. The downhill, let's talk just briefly about that downhill. What happens once you've reached that transition state? the downhill, the side on the other side. This relates to the amount of energy, relates to amount of energy released when new bonds form. Released when new bonds form. Now what you can do is you can compare the amount of activation energy to the amount of energy released when new bonds form. It would help if I could write the word form. There we go. And we can see what's going to happen. We can see if this is going to be beneficial for that reaction to take place, or if it's unlikely for that reaction to take place. So those are a couple of theories for you. We're going to start next time by talking about reaction mechanisms. I will see you then.